Also because in reality this drawdown could end up being even higher due to possibly unfavorable conditions like slippage, spreads, the broker, or maybe some news events. We could even reach higher drawdowns, but by starting from such a low value, we can be confident that we can absorb them easily without blowing up the account. We can see here, in fact, that in the next row, I calculated the percentage standard deviation relative to the drawdown. In my case, I have 1.67% overall and 1.45% in out of sample. I need the standard deviation because I use this standard deviation to calculate increased drawdowns with a certain probability that this drawdown will actually be reached. So I have what is called a standard deviation, and I calculate it in the following way, by taking my drawdown plus 1 time the standard deviation. Then the second thing I do is I have a 95% probability of staying within this value, so I add 1.96 sigma, which is the standard deviation, and so on. The last value, which is basically the limit, thank you, I have a probability of staying within this value of 99.7%. What does that mean? It means I only have a residual 0.3% chance of exceeding this drawdown, which is still 16%, so all things considered, it's reasonable. Is it possible to reduce this risk? No, because anyway, a model can't be built on such a restrictive condition that is still eventually reached. Only in 0.3% of cases, meaning it would be excessive to focus solely on this eventuality because this is a catastrophic event, and yes, it's accounted for, but the probability of it actually happening is really low, since 0.3% is a low probability. These are data that I can then also cross-reference with the results from the Monte Carlo analysis I did on Quant Analyzer. In this case, the data are quite similar, so we can take a look, and between the two, if we want, we can choose the worst case between the Monte Carlo and this 99.7% probability of drawdown.